Alrighty, welcome back to 353. All right, so first off, let's start. This is the start of week 2. Let's start off by a little bit of a review. So, we learned that there are processes which are kind of like a running instance of our program, which we can have multiple of. So, let's draw a box that represents our process. What are some things in a process that we need to keep track of a running program or allow a program to run? Nothing? A program can run with nothing? Yeah. Stack. All right, we got a stack somewhere. Anything else? Yeah. A heap. All right, we got a heap. Yeah. We got registers. Are they real registers? Sorry?
They're real registers.
No. Yeah. Well, we got virtual memory. Yeah. So virtual memory is a good one. So we got virtual memory. And technically, that's where the stack and the heap also live, right? Then we also have some virtual registers. All right, is that all we need to run a program? Registers, stack, heap? Well, I guess that's all we need for now, but our Hello World program, right? We outputted Hello World to something. Anyone remember what that something was called? The magical number we used, we gave it a name, ish. Yeah, guessing no? So, file descriptors. So, program probably interacts with something else. So, technically we have some, technically they're open file descriptors. We didn't go into it too much other than saying, you know, basically it's representing some resources. So let's have a nice division here. So processes are managed by the kernel, so they would be in kernel space. And then if we have kernel space, what's the other thing called? What do our applications run in? User space, right? So we got user space up here. And this is where our applications live. Oops. How does an application try and make a request to kernel space? Yeah. System calls, right? So crossing this boundary is done with a system call. All right. So other little things. So this is a bit beyond, but we can imagine that the kernel is also keeping track of like a whole bunch of files. So maybe we got file 1, file 2, maybe something representing our terminal. So open file descriptors for a process, you can think of it for now is in your process, there is just a big array of pointers to files. So these are your open file descriptors. And a file descriptor is basically an index into that array. So the default ones, or by convention, there should be a 0, 1, and 2. So the way to think of those file descriptors are they're kept track in your process and they point to some resource in the kernel. Could be a real file, could be something like a terminal. So for instance, by default, something that again is a bit beyond is that the default file descriptors 0, 1, and 2, they all point to this terminal resource that we can read bytes from or write bytes to. Other thing to tie it together, we also talked about libraries. Where do libraries fit in on this picture? We don't need them, screw them. Yeah.
Doesn't it depend on the specific system, what side they were in?
Nope. Yeah, answer was, doesn't it depend what kind of architecture? So the architecture of the kernel decides what's in kernel space and what's in user space. Typically, that has to do with things that are kind of related to the hardware. Libraries usually aren't super related to the hardware. Yeah?
They're at the bottom of the user space?
Bottom of the user space, yeah. So libraries are somewhere in user space. What libraries you would consider part of the operating system depends on what applications you're running, but they would be in user space. Typically, these system calls, you don't do just using that ABI we saw before. You can do that, but how we're going to use system calls in this course is the library we use, the standard C library or other POSIX wrappers will do the system calls for us, or maybe add some other features like that @exit thing and all of that. So our applications will use libraries. They could directly do system calls. Usually that doesn't happen. Libraries give you some added functionality. They may or may not do a system call, group up system calls, add new features, everything like that. And what we're concerned about kind of in this course is this whole system call boundary here between programs. So we'll be creating applications that pretty much use the system calls, but use the C wrappers, so they're a bit easier. And we should be able to explain what the hell is going on in kernel space. You might imagine writing kernel space code is difficult because it has access to all the hardware and things can go very, very wrong. So we'll stick to user space for actually writing stuff. So any questions about the whirlwind of week 1? Because it is going to get very strange today. All right, everyone ready for it to be weird? So this is where the course starts getting hard. What you know about programming is about to be turned on its head a little bit, and it's going to get confusing, and it's going to stay confusing for about, I don't know, 5 weeks, and then we'll figure it out. So bear with me, ask questions. We know just enough to start being dangerous after this class, and you'll probably crash my computer at some point. So we're going to start talking about processes. Again, here is the process representing a running instance of our program. I can have multiple processes all running the same program independently, like we saw with that count example. So here's me just adding open file descriptors to that process, which is basically just an array of pointers to some resources that you can read bytes from or write bytes to. So technically, all the information about a process is in something called a process control block, or of course we need a TLA for it. So it's also called a PCB that contains all the information you want to know about a process. Specifically in Linux, they call it the task struct, and you can browse it on GitHub. Great thing about the Linux kernel is it's open source, so you can read all about it if you want to see what exactly makes up a process. All we really care is that it contains some process state, saves the CPU registers, so like a copy of those virtual registers, has scheduling information, like when this process should actually physically run on a core, which we'll get into a bit later in the course. Memory management information, so what its virtual memory is mapped to in physical memory. Again, topic later in the course. I/O status information, so if it's reading or writing from a file or a network connection or something like that, and lots of other type of boring accounting information. The thing we really need to know so far is that each process gets a unique process ID. Again, we shorten it to just be PID or process ID, and that's in order to keep track of a running instance of a program, so it is unique as long as that program is running. So processes have a lifetime, right? We run our program, it ends. So if we want to really break down the lifetime of a process, we could do it with a handy dandy state diagram. So at some point, which we'll see today, we can create a process out of thin air. It is creatively in this created state where the kernel has to go ahead, set aside some memory for it, set it up so that it's able to execute, give it space for a stack, maybe load the program into memory, things of that nature. And then once it's ready to execute, it will transition to this waiting state, which you could also rename it to ready if you want. It means it is able to run, but the kernel has not deemed it important enough to actually execute on a CPU. When it deems it important enough to actually run on a CPU, it will transition from waiting to running, where it will actually physically run on a CPU core. So the kernel would have to load its previous version of the registers and everything like that, let it get access to the CPU and actually physically run. So if our program is short, it will transition from this running state to this terminated state. And it will do that using that exit system call, right? So it will do that. That means our process is done. It's terminated. It's done running, so we can clean it up. If our program runs for a long time, well, especially I have like hundreds of processes on my machine, your kernel is going to be smart enough to be like, okay, well, one of the other 99 processes, they get a turn at the CPU, so it will stop you from running, save the current state of your registers and everything like that, and put you back in this waiting state where you could execute again on the same CPU core, maybe a different one. Again, topic a bit later in the course. But it might deem you important enough that, hey, now it's your turn again, you should run again. And then you could run. Then maybe you make a system call which is slow or needs to do some I/O or something like that. So if you make a system call, your process will go from this running state to something called blocked. Blocked means it's just waiting for the kernel to essentially finish a system call. So it will go to this block state. Maybe it's waiting from input from a file. Maybe it's waiting for input from a terminal. Maybe it's waiting for input from a network, something like that. So blocked means it's not able to execute. It's not terminated. It's waiting for something to happen. So after something happens, I get that data from the slow disk or something like that, it will transition back from blocked to waiting or ready where it's able to execute again, and then we could run it again. So any questions about that fun state diagram? Yeah?
Does block correspond to one process ID?
Yeah, so this is just for a single process. So one process can be blocked. And we'll see how to figure this out to see processes that are blocked on Linux and all sorts of fun stuff. All right, so you can read process state information using this proc file system on Linux. So there's a standard proc directory specifically on Linux that represents the kernel's state. So they aren't real files, they just look like it. So every directory that's a number represents a process ID in that proc file system. And within that directory, there's a file called status that contains the state. And that's used for Lab 1. Everyone's used Task Manager or Activity Monitor on Mac, right? That shows you everything running. Well, Lab 1, you're going to create a slightly scuffed version of that that works on Linux. So you're going to write your own kind of process viewer. So if we take a look, just to explore a lit, if I do ls in this proc directory, I'll see a whole bunch of things that represent the state of the kernel, something zone info, VM alloc info, uptime version, interrupts, file systems, like a whole bunch of different file names. Fun one might be like, hey, there's one called CPU info that if you read it will tell you what CPU you're currently running on. And then all these directories that are numbers represent a process running. So if it's all numbers, that is the process ID of that process. So for instance, if I wanted to, I could look, ignore weird names there for now. If I looked at, there's a process called process ID 1. If I looked in here, there's all sorts of information that I could see about process ID 1. Most important one, only one we'll use for Lab 1 once it's posted tomorrow, is this status. So if I look, that's a file. So if I cat the status file, I can see a whole bunch of information about the process, including its name. It's called something called systemd. something called, there's a UMass, there's a state, so it's currently sleeping. Isn't that cute? And it has a whole bunch of information about it. Process ID, we'll see what this number means in a bit, but it's got a whole bunch of information about it, including a whole bunch of stuff about the memory and all that. But it's a way to actually view what the kernel is telling us. There's a few other fun things in the proc file system, like this proc CPU info. If you want to look at it, it will tell you how many cores you have on your machine and what they are. So on mine, it's an ARM because it's running on my MacBook, so it doesn't have too much information. The CPU implementer, they didn't want to say Apple, it's 6.1. Ooh, fun. All right, so that is our whirlwind tour of that proc file system and a little review of what you'll be doing for Lab 1, writing a process manager. So how to actually create processes. I could create them from scratch, load a program into memory, create that process control block. That's what Windows does all in one shot. Unix, for historical reasons, decomposes process creation into more flexible abstractions, although there's arguments that I also would make that they're becoming increasingly bad with threads, but we're going to roll with it for now. We'll see why it's bad once we get to threads. So for programs with threads, typically this decomposition of process creation is going to be a bad thing. So for programs, there's a way to do it on Linux like what Windows does using something called POSIX spawn, which will just create a process out of nowhere. But what old historical Unix does, instead of creating a new process from scratch, it could just clone the current running one. So what this does is pause the current running process, copy its process control block to a new one. This reuses all information about the process, including variables. So the new process is an exact clone of whoever created it. They are, aside from their process IDs, otherwise identical. And the way Unix distinguishes between these two processes is with something called a parent-child relationship. The metaphors are going to get quite literal here, and it's going to get quite messy. But our first one is parent-child. So like if you have a child, it's kind of like a clone of you. So the one who created it is the parent, and the newly created process is called the child. So after that point, there are two separate processes that operate independently, and they can both execute different parts of the program together, maybe in parallel, maybe concurrently, which they might mean the same thing to you right now, but as we go on, we will distinguish what they mean. So this new process, sometimes it can either just continue running as a clone, or it can load the new program if I wanted to indeed run a new program. So in order to create a new process, it's not called give birth to or something like that, even though it's parent-child. They called it fork. So fork creates a new process, which is a copy of the current running one. So its API is fork, takes no arguments, and returns an integer. And the way it works is it returns the process ID of the newly created child process. The only time when that is not true is if there is a failure. So if it fails, it will return -1. If it returns 0, it will return 0 in the child process. So the only way to distinguish between which process is the original and which is the clone is the return value of fork. So in the child process, fork will return 0. And in the parent process, fork will return a positive number greater than 0, which will be the process ID of the child. Yeah?
What does in the mean in this case?
So in the program that's running, in that process. If that makes it, we'll have an example. So we'll write a program for it. So it's going to get a bit weird, because now there's two processes running. They can access the same variables, but they're completely independent and completely separate. And you might think this is a complete waste. Like what if, Chrome running with 2 gigabytes of memory, cloned itself when I have to copy 2 gigabytes of memory. So operating system do something called copy on write to maximize sharing to make forking really, really, really fast. So you don't actually have to copy 2 gigabytes of memory. But again, we won't go into that until we start talking about how to manage virtual memory. So as an aside, before we get into our example, is on POSIX systems, you can find documentation using the man command, short for manual. We always have to make it shorter. Today, we'll be using the following APIs: fork, execve, and wait. We're going to do that today, so don't worry about it. So you can use man function to look up the documentation. Sometimes, if you just do man and then the function name, you'll get something weird, so you might have to specify a number. The number 2 is for system calls, and the number 3 is for library calls. So for instance, if I do man fork, well, I get the correct one, so it tells me all about the C standard library fork, which is good. Creates a new process by duplicating the calling process. Thank you. But if I give it something like execve, whoops, execve, oh, that gives me the right one. So maybe it gives me the wrong one if I use read. Oh, OK. So this gives me the read for my shell, not the read, the system call read. So if I wanted to look up the documentation for the system call read or the library wrapper, I could do man3 read, not in section 3. So I have to do section 2, which is the system call. And then I can actually look at the documentation for the system call read. So if you don't get the right thing using the man page, you can do this, or you can look it up on the internet. All right, so let's look at our first fork example. And again, ask questions because things will get slightly strange. All right, so here is our program. Let me clear this and make sure we can read it. So starting off, rules are exactly the same as we all know and love. So execution starts at main. In this case, we now know that technically a process is running this program. It will get assigned some random process ID. So if I want to mark where I'm currently running in my program, I can mark it by saying where this process is. So each process will get a number. I'll just, for argument's sake, say that this process running main is process 100. So I'll just shorthand it and write it at P100. So here, the first thing it does is call fork, which is where things immediately start getting weird. And again, ask questions because we're going to try and run this. So after I call fork, I have now created a new process, which is an exact clone of the calling process. So I'm going to create a process, let's say, for argument's sake, it's called process 101. So it's a new process, and the only difference is the return value of fork. So in process 100, fork returns the process ID of the newly created process, so it's going to return 101. And in process 101, so that is the clone, fork is going to return 0. Yeah, let's say returns. So knowing that now, so I cover the error case here, so we can ignore that for now. So let's just argue about these two else statements. So one says if our program still runs as normal C programs do. If it takes the if branch, it'll just take the if branch, do those prints, and then fall through the if branch. And I don't show it at the bottom here, but it just returns from main and just terminates. So I have an if and an else if branch. So now if I run this program, what will I see? Any guesses? All right, first off, easier question. How many lines are going to get printed? 6, 3, 3. We got a whole bunch of 3s. All right. Good, because this is where our brains will start hurting. So we run this program. We get 6 lines. Why do we get 6 lines? Well, because now, since we cloned ourselves, we now have 2 processes. They're both running independently, and one process, in this case, process 100. So fork returns 101 for it. So after the fork, they operate independently. So process 100 is going to create a variable called return ID, assign the value 101 to it. So is 101 greater than 0? Yes. So process 100 will go into this if branch and then print off these 3 lines and then exit. And now that process is done. But we're not done yet because there is another process to run. So process 101, which is our clone, fork returns 0. So it would also be a copy at the time of the fork, which just means it's running main. And then it would return from fork, return 0. So it would create a variable called return PID, assign 0 to it. And then is 0 equal to 0? Well, yes. Now this process, 101, will run this. And then it will print these 3 lines, child return PID, then the value of its variable. And you can see all the lines aside from it saying parent or child print the exact same copies of the variables. So this returns the value of return PID, which is set from fork. This system call called getPID, that gets the process ID of the current running process. And getPPID, again, I don't know why we need to make everything so short. That stands for get parent's process ID. Yeah?
So when the child process calls fork, why wouldn't that create another new process?
The child does not call fork. Only the parent calls fork. And then it's like, then the child gets created as an exact copy of the parent, and then it returns, it looks like it just returns from the fork. So only the original process that started running main created that child. So it only creates one process.
So the child process actually starts running not like starting from the top of the main program, but starting from like wherever fork branches off.
Yeah, so the child process basically started running at fork. And it started running, its initial state was an exact copy of the parent. So it starts running, you can think of it as the child starts running at fork, and the only way to distinguish it from the parent is what it returns from fork.
Okay.
Yeah?
Will it always run like parent first, then child?
Yeah, that's a good question. Will it always run parent first, then child? Well, ain't nothing to it, but to do it, we can just run it a few times. Whoops. Let's see how unlucky we get. There we go. So the answer to that is no. So turned out that I can't argue about which process runs, because which process runs is determined by my operating system, right? It gets to decide what to run. It just so happens that most of the time, parent prints 3 lines first, and then child prints 3 lines. But because they're 2 independent processes, you don't know which one runs at any point. So within a process, your mind does not break. So within the main process, or the parent process, it will still print these 3 lines in order. So it will always print parent return, then parent PID, then parent PID. But there's no ordering between 2 different processes. Your kernel gets to decide what to run. So it could print parent child, parent child, parent child. There's no order between the processes whatsoever, which is our first brain-breaking thing, because you might actually want some type of order here. But we'll get into that much later in the course. Yeah?
So it was just lucky then that it printed parent.
Yep.
Parent child.
Completely lucky that it was always parent and then child. Yeah?
So does fork always create a parent and a child?
No, so fork always creates one new process. So I had a process that was running main. In this case, I argued that was called process 100. And then fork created one new process, and it was 101. So I had something running, it called fork, it created a new program.
So you ran main before?
Yeah, so when I ran my program, right, something created a new process and started running this program, right? That I don't know quite what it is. We can explore and see what it is, but something started running that and created a process to run that program. And then immediately I created a new process from that running.
So fork just creates the child.
Yeah, fork just created one new process. So let's run this here. So the numbers are also consistent here. So parent return PID, this is the return value from the fork. So in this case, it was 5515. So if I look at the process ID of the child, it should kind of jive, right? That should be the process ID of the child. And I can see that indeed in the child, fork returned 0, and the child's process ID from this get PID call is 5515. So that makes sense. It is clearly the child of the original parent process. And then I can also check that all my numbers jive. The child's parent process ID is 5514, which is the same thing as the parent's process ID, right? So all the numbers kind of make sense. So yeah.
Okay, so for return PID, why is it greater than 0 in the first in the first condition and then it's equal to 0 in the second condition?
So return PID, why is it greater than 0 in return?
Yeah, so why does it go into both if and else if?
So your brain hasn't broken, a program did not go both into the else and the if branch. So that didn't happen. You're not allowed to do that. What happened is because of the fork, we have two instances of this program running, right? So we have a process 100 and a 101. So within the process, it still obeys all the C rules. So process 100 went into this if branch, and process 101 went into this else if branch. So within a process, all the rules still apply, but yeah, you're right. At first glance, it looks like, if you just run it and look at the output, it looks like, if you didn't know what a process was, it looks like it just did the impossible, right? But trust me, first thing is that the impossible does not happen. I have two processes. Yeah?
Can fork create a child from, like a new process from your child?
Like, can I call fork again? Yep. That's where things get interesting. So the question is, can I just fork again like this? So any guesses as to what happens if I just call fork again like that? Yeah. Yeah.
Here,
Yeah, sure. Yeah.
I think the parent is going to create another child, and then the child is also going to create another child. So now we're going to have 4 total processes.
Yeah, so if I do this, things are going to start getting weird. So let's see if we can argue about what it does because it gets more complicated. So we'll rewind and say something created a new process that is running main. We'll call it process 100. So process 100 calls fork. So because of it calling the first fork, it would create a process 101. And then the return of fork returns 101. And in here, fork returns 0. And then the next thing they do is returned PID will be equal to 101. And then if it executes return, PID will be equal to 0. Right? So now I have two processes running. I don't know technically what will run next. It's up to my operating system. If process 100 runs next, it would call this fork, and then it would create something like process 102, which is an exact copy of itself, right? So it would also have a variable called return PID, and it would be equal to 101. The only way to distinguish between them is the return value of fork, which I conveniently just throw away. So they are now indistinguishable clones of each other. So in process 102, it has a variable called return PID, which existed before the fork, so it exists after the fork. So it would have a variable called return PID that is equal to 101. So both process 100 and 102 will go into this if branch, print a whole bunch of things, and then eventually, so let's just assume that they ran. So they went into here, printed a whole bunch of stuff, and then let's say process 101 executed. It called fork. It would create something maybe called process 103, so a new number that's not used. And it would be an exact clone of whoever called fork, which in this case would be process 101. So it would have a variable called returned PID, not return, and it would be equal to 0. And then I don't use the return value of the fork or anything like that, so they're indistinguishable clones from each other. So they would both go into the else branch. So when I run this, I should see 6 lines that start with parent and 6 lines that start with child. So let's go ahead and run this. Boom. Lots of confusing stuff. Fun, right? Isn't that fun? Aren't our lives complicated now? Yeah.
Why does like P100 when you fork it like the second time? Why does that not make a child that has like a 0 PID? Why does that make one like a 101?
Oh, so the question is, when 101 created a process, why didn't it create a child with like 0 from fork?
When 100 made a.
When 100 made a, yeah, so let's rewind. So we want to rewind back to, it kind of looked like here and we just had process 100, right?
Yeah, like if you had the second fork and then 100 made 102, why doesn't the return one have 0? Because when you first forked the parent, it had one that was 0.
Yeah,
So when you fork it again, why is it?
so when process 100 calls fork again, it creates 102. So fork here will return 102. So this fork that process 100 does, the second one, this fork returns 102, the newly created process, but I don't use the return value, right? I just throw it away. And then process 102, which is the newly created one, it appears as if it starts executing returning from fork, and it gets returned 0. But again, I just throw it away. So I immediately throw it away. So if I captured it in a variable, then yeah, it would be 0, but I just threw it away, which makes it, if I throw it away, I basically can't distinguish between them unless I like get the process ID and figure it out using that. Yeah? How does fork know the difference between the child and the parent? Because fork is a system call, and one process made the system call, so that is the parent. The one the kernel created is the child.
So when 100 makes the call, and then.
Yeah, when 100 makes the call, that's the process that made the call, so it's the parent.
And then 101 also makes another call.
Yeah, so if I was to draw like a family tree, in this case I have a bit of a weird family tree. So process 100 was the original one, right? So technically process 100 created 2 children, right? It created process 101, and then, what a good ASCII diagram. It also created process 102, right? And then technically process 101, that called fork, the second fork, created a process called 103. So this would be like my family tree. So for the family tree, the parent, it's always like the parent at the top and then arrow to the child. So process 100 created 2 processes. One was 101, the other was 102. So it had 2 children. And then process 101 created a process called 103. You could think of it as like, process 103 is like the grandchild of process 100 if we wanted to be super literal. Yeah?
same return value as 100.
So before this fork here, right, there was a variable called return PID, and it was equal to something. So because a fork creates an exact clone, that new process is going to have that exact variable equal to that exact value. So that's why. So I didn't reset it, I didn't reassign it. It just got cloned. That's why in process 102, so for the second fork, by the time I called this fork, there's a variable called return PID. It was equal to the value 101. So if I call fork, I create a new process. That's an exact clone at the time of the fork. So has the same variable equal to the same value. Yeah?
So return PID is only different for the first fork call. After that, the variable state gets saved.
Yeah, so
The next fork is the same.
in this case, I only assign the value return PID after the fork, and then I don't update it again, so it stays the same. All right, that's where it gets slightly complicated. Let's rewind a bit. So any questions about just the normal one, or anything where you're curious about? So all the numbers kind of jive. Oh, look, all the child printed way before the parent that time. That was fun, huh? Yeah.
So when you initially had like nothing running,
Yeah.
the first call to fork will return 101.
Yeah.
Doesn't fork create a child
Yeah, so process 101 is the child
of
of 100.
then how did it get 100?
Oh, well, we can explore. So the question is, how did that process get process ID 100? So in terms of real numbers from running it, this is the parent process ID, right? In this case, it is 5,090 or 915. So you're asking, basically, what created this process, right? Well, I have that process's parent ID, and it's that number, right? So that means my parent is that. So that must have created me, right?
Was that a call to the fork in this function?
No, so this is the process that created me that's running this main function initially.
And somehow that value got assigned to return PID.
Somehow that value got assigned to return PID.
5915 must have been assigned to return PID.
5115?
5915.
51.
Like otherwise, it wouldn't have been printed in like the first if statement.
There's no 5195. 5915?
Yeah, 591.
5915. So, yeah, this is 5915 is the process ID of my program running main. And something had to create me, right? So that thing that created me is this process ID. So this fork, right? I created a new process. I created this process. I created process 1516. So this process was created from me from the fork. I only created one process if I have this program. Something must have created a process to run this main function initially, right? So if I wanted to explore what created my process to run this program, how would I do that? Or AKA, what the hell? How would we explore what the hell this is? Because this had to create me, right? 4015, that created me. Any guesses as to what the hell 4051 is? Yeah. The process for the shell. That is a good guess. How would I verify my guess? Well, there's that whole proc file system I could look at, right? So I could do less proc. If I wanted to do it kind of scuff version, I could just do the number. So the number is the process ID. So I can figure out what 4051 is. And I can look at the status file. And it will tell me that the name is fish. So fish created me. What's fish? It's a shell. So it's a shell. For you, it might be bash, it might be ZSH, whatever, so it's a shell. But this kind of makes sense because, well, what I'm typing in to run my program is the shell. So the shell created a copy of itself, must have created a copy of itself because that's the only way to create a new process. And instead of running a copy of itself, it started running my main instead. Kind of cool, right? Well, how the hell did it start running a different program? So what shell must have done is use something like this exec VE system call. So what that does is it replaces the process with another program, resets the process control block, and starts executing that program instead. It has the following API where it needs a path name, so that's the full name of the program to load. argv, which is an array of strings, which is an array of characters, terminated by a null pointer that represents the arguments to pass to the process. np is the same as argp, but that represents the environment of a process. We won't get into really in that course, but it's basically just global variables. And then it also returns an error on a failure, does not return if it's successful. So let's get into that example. So if I don't combine it with fork or anything like that, so if I run this program, it starts executing main. Thankfully, I don't have a fork in this, so nothing weird happens. So it's going to execute how I expect it to. It's going to printf, I'm going to become another process. Then it's going to fill up this argv array. So that's all like the command line arguments you should give it. By convention, argument 0 should be the name of the program that you actually typed. So let's kind of simulate actually running ls. So the first argument is ls. And then you give it a null pointer to signify that is the end of the argument list. Then there's np. I'll just set it equal to null to indicate that there's nothing. Then I do exec VE. So I give it the path to the executable to run. In this case, I want to run ls. It's an executable. It's just an elf file. Then I give it the argument, then the environment p. And then if I look at the API, it returns -1 if there's an error. If it is successful, this process starts running that program instead. So that process ID just gets reused. This program stops running, and the process runs a different program. So it will maintain the same process ID, but in this case, it will turn into ls and start executing ls's main. So if ls is found, I should only see I'm going to become another process. Then I should see the output of ls. So I shouldn't see any error. And if exec VE worked, this line will never print because I'm running a different program instead. So if I run this now, I should see I'm going to become another process, and then I see the output of ls. So this, if it was created as process 100, then ls would be running as process 100 after that exec VE system call, and then runs that process. As soon as ls exits, that process is dead, and we're all good. So questions about this fun thing? Yeah?
So the reason we put ls in the args is because you just have to include the program name as the first argument?
Yeah, so the name here is just purely by convention. So if I wanted to, I could actually do this if I wanted to. Null, that's fine. So compile it, run it, nothing bad happens. Turns out, you could have just made a lot of money by exploiting sudo. Everyone's used sudo before, right? So sudo lets you run as root, does a whole bunch of checks and everything like that. So that having an argument there that's the name of the program is just by convention, usually to help you print a help message or something like that, but it doesn't have to be there. The developers of sudo just assume that it's always set. There's always at least one argument that's the name of the program. So if someone did something like that where they passed it null, and then sudo used it without checking, so they dereferenced the null pointer, which segfaults or corrupts memory. And if you were clever enough, you could corrupt memory in such a way that you could take over sudo, get a root shell, and then boom, you own a system because they didn't check that the first argument could actually be null and not exist. So fun security fact, but it's just by convention that the first thing should be an argument, or the name of the program. Whoops, I called it loss. All right, any other questions about this? Yeah?
So if Fish wants to execute my program, it first needs to fork, and then in the child process it needs to do execute, right?
Yeah. Yeah, so if I was to, so this just replaces the current process. So if I was Fish, right, and I just did exec VE, then whatever you're typing in is now poof, gone. It started running a different program, right? So if I wanted to basically write my own shell, I could do what I did before. I could just fork, and then I could have if PID is equal to 0. It's harder to type on this than I thought. If PID is equal to 0, then I could do all this, right? So that would mean in the child, it does all this, and then the child transforms into some program running ls. So in this case, if I run this, let's indent it so it doesn't look as ugly. So in this case, I will actually see if exec-v work, this line will never print because my child started executing ls, right? So let's just make sure I'm not crazy and that that works. So compile it, run it, and then I see, in this case, the printf lines are a bit out of order because, well, it's consistent within a process. So the parent printed, I'm going to become another process, and then create a child. The child is set up to run ls, but didn't quite get there yet. The parent continued running and said, if VXC worked, this line will never print, and then terminated itself. And then the new child process, that's the one that ran ls. So this is basically how your shell works, right? It forks itself, it sounds bad, and then it execs your program, whatever you typed in the terminal. So that's how your program, well, that's how we actually run your program. Yep. So why does it run simultaneously? So by default, I have no choice. I have no control over what runs first. In my shell, it like waits for that command to finish, right? So we'll see how to do that after the break. So that's something we can do. All right, any other fun questions? Let's rewind. Before fork things up. All right, any other questions for this? Or weird things? So another question I usually get is like, why the hell is ls repeated twice? Doesn't that sound silly? So turns out this convention is actually used for quite a things. Everyone's done like, you know, -- help for something, right? So like ls -- help, right? That prints something, gives you a help message, and like tells you, let's scroll up, like tells you a whole bunch of things about its usage, like ls and a whole bunch of files. Well, it turns out that the name of the program doesn't have to correspond with what you actually typed in your terminal, right? I could have made an alias or done something weird. So turns out that is by convention to kind of help with error messages. So if I wanted to simulate running help as like exec VE, I could do like, you know, name it whatever the hell I want, and then do -- help, and that should do the exact same thing. So if I compile and run this, get the help message like before, but as I can see, by convention, it actually uses that to try and give you more descriptive names. So it pulls the name from the first argument, not the name of the executable, because it doesn't know anything about it. So that's just by convention. You can call it whatever the hell you want. In fact, some programs actually use that to behave differently depending on what you invoke it as. So like some core utilities that implement CP and RM and all those move commands and everything like that, It's the same executable that behaves differently depending on what name you call it as, but it's the same actual executable. So you can do something like that. Usually by convention, it's just to help with the help program name. I don't know. But knowing that, you can do fun, stupid things like that. All right, any other questions about that? We'll see how to develop a shell after our break. Oh, yeah? Oh, the index equal to, so this index equal to stuff are my code completion thing. I didn't actually write them in. It's just to tell me what the value is at index 1, 2, things. It's just a code completion helper. All right, so that was fun. Now programs don't seem to, do what we think them to. So for a break, we'll leave on this note that the operating system creates processes. Operating system or the kernel has to maintain process control blocks, including some state, create some new processes. Now we know what system call does that, fork. And we have to load a program, reinitialize a process with the context. That's exec VE. So we're going to see some more fun things, more fun terminology after our break. So let's take our break now. Whoops. Alrighty, so mic on. All right, let's continue our journey into processes. So we have parents, we have children. Things are going to get even weirder. At the end of this lecture, we're going to have zombies, orphans, which in later lectures we get to kill, so we'll have fun. So your Google searches are about to get a whole lot weirder. Try not to get on a list. So we saw that process state diagram before, created to ready to blocked. So Linux has that same diagram, but the terminology is slightly different. So if you were observant, you can read the process's state by looking at that status file again. There is a field called state, where again, I can replace PID by the process ID, or if I wanted to have a shortcut, I can replace that PID with self, and that gets the process ID of the current running process. And the Linux states are as follows. So there's a runnable or running state. That's the same as when I showed before, running and waiting or ready. Linux does not consider ready and running to be different. It groups them all in this running or runnable state. Then it takes this block state and divides it into two types of blocks. So again, blocked is like you're doing a system call. The kernel is trying to do something for you. So there are two types of reasons that you are doing a system call. And the first one is called interruptible sleep. That is one kind of block. That means you could get woken up and resume execution if you wanted to. You're not actually waiting on anything important. You kind of opted in to go to sleep, so someone could wake you up and then you could actually do something. Uninterruptible sleep is like me if you don't have coffee. I'm asleep, I'm busy doing something, in this case sleeping, and even if you tried to wake me up, I'm not going to do anything useful. I'm going to ignore you. So technically on Linux, uninterruptible sleep is you're blocked waiting for something and you can't get woken up to resume to do anything useful. Usually it's because you're waiting on output from a file and it's assuming you actually need that output to continue. So since the output is not available, it will be in this uninterruptible sleep state where even if it wanted to try and wake you up, you couldn't do anything useful anyways. So you will just stay blocked forever. There's no option to wake you up. So the other state is a state called stopped, which we'll see in the next lecture. And then there's also this zombie state. So we're going to see what this zombie state means because it is a real state name in Linux, and it seems kind of weird that something would call you a zombie. So this stop state is because the kernel lets you explicitly stop a process if you want to prevent it from running. And then another process can explicitly continue it. But we'll see how to do that in the next lecture. So also kind of the infrastructure, why we have this parent-child relationship on and everything is because on Unix, so Linux or Mac OS, the kernel, when you boot up your machine, it is technically only responsible for one job for user space. It launches a single user process, and then that process is responsible for creating every single other process on your machine, either directly or indirectly. So it has a special name. It's typically called init. The kernel, when it boots up, will look for it in the folder sbin init. And again, it's responsible for creating every single other process on your machine. It must always be active. If it exits, the kernel thinks you're shutting down because it's supposed to be, if you want to think of it as like the grandparent of every single other process, and it should outlive everyone. So for Linux, init will probably be something called systemd, but there's some other options. So when I looked at the name of process ID 1 earlier, its name was systemd. That is the name of an init system. There are more or less religious wars over what init system is the best. There's a whole bunch of different options. You could even write your own if you really wanted to. So also, as an aside, some operating systems like Windows create like an idle fake process that basically the scheduler can run just to keep track of how much time your CPUs are idle for and not doing anything useful. So we kind of argued that there's parent-child relationships between every single process. So if I wanted to see that process tree that we kind of drew before on a virtual machine or your container, you can actually view it. It probably looks something like this. So there is a command for it. If I want to see the process tree, whoops, let's expand this window. I can use something called htop, and that will essentially be like a command line process viewer that will show you some more information. So above here, it shows me all the CPUs I have, what % usage they all have. So right now, my system's pretty much idle. Shows me how much memory I have. And then it shows me a whole bunch of processes running on my machine. So by the end of this course, we'll be able to read all of the columns. But for now, all we can read is the process ID. So the first one is process ID 1. So that is init. And then it tells you the command used to run it. So it's something called systemd. And then it has a line from it. So it will tell you all of its direct children. So it created some children. It is going to be the grandchild or grandparent of every other process. Either its direct children or every other process will be related to it somehow. So it created directly journald system or user dbd, and then it created a whole bunch of other subprocesses, created a whole bunch of other things. I can look through it. There's this low memory monitor. That's probably a good process to have. If I go through it, there's some dumpy things, some other things, but you can see that every other process is related to this. Let's see if we can find something. So here, GNOME shell, that is the desktop environment I'm writing in. So it's running as a process. And when I launch VS Code through my desktop environment, well, it had to fork itself. Again, wow, that sounds bad. So it forked itself. It exec VS Code, which is called code. So I can see that the shell created VS Code. So this is VS Code. And then VS Code went crazy creating subprocesses. So it created some processes to use as a sandbox, created a whole bunch of processes. One of the processes it's created is the shell I'm currently typing into. And then, hey, look at that. I can see htop. So this is the command I'm currently running to view itself. So this is the process ID of this. And then I can also see what's the fun. So there's command. It's a really long command. All right, maybe it doesn't show the state. So anyways, you can see all of the parent-child relationships between all of your processes on your machine. Yeah, there's nothing else terribly interesting here yet. So you can explore that and have fun with that. Whoops, I exited the wrong process. All right. So go back. Let's make sure this works. Nope. All right, recovered. All right, so processes, they just get assigned a process ID or PID whenever they're created, and it does not change as long as they're running. Remember, process ID is just a number, and it is unique for every active process. On most Linux systems, there's a maximum PID of like 32,000. 0 is reserved for being invalid because, well, that's how fork knows that you are the clone, you're the child process. So eventually, the kernel will recycle process IDs after the processes dies for that new processes. It happened that my processes, I got process IDs in the same order, but that's because I rebooted my machine recently, so I haven't gone and recycled any process IDs. So they might not necessarily be sequential. And also remember, each process has its own address space, so independent view of memory. So each process behaves how you know C programs work. It's just now, instead of having one process you get to argue about, multiple maybe going on at the same time, and you don't know which one executes when. And also had the question during the break, another way to think about fork, another good way to think about fork, or how I like to think about fork, is one process calls fork and two processes return from fork. That's another way you can think about fork. So you might be wondering, hey, if I can terminate a process, what happens to this parent-child relationship? So previously, you didn't notice, but there was a little sleep there. So I made sure that the parent exited last by cheating a bit and using the sleep. So Linux or Unix is very, very serious about maintaining this parent-child relationship between processes. And if one can exit, so one can disappear, one can cease to exist. So what happens if a process exits first and no longer exists? What happens to that? So the reason we have this is, like in real life, the parent is responsible for its child. So the operating system, whenever you terminate a process, the system sets the exit status when that process terminates and records it in that process control block. So whenever you terminate a process, the operating system can't clean up all the resources because, well, something has to acknowledge it and actually read that exit status. So the minimum acknowledgement the parent has to do for the child is to read its exit status, or to read whatever it gave to exit or return from main. So there's actually two situations if one of the processes exits. So either the child exits first. If the child exits first, then that child process becomes something called a zombie process because, well, the operating system can't run that program anymore. It's terminated, so it's technically dead, but it's still alive in a way because it can't remove its process control block because someone has not acknowledged it yet. So it's both kind of alive and kind of dead, kind of like a zombie, which is why they named it a zombie. They give things dumb names. So again, quite literal. Speaking of literal names, if the parent exits first, so you create a child and then you terminate first, your child now no longer has a parent. Gruesome, eh? And, well, they use the literal name of that child process you created is now technically an orphan process because its parent now doesn't exist anymore. So there are rules with Linux or Unix what to do in these situations. So if all goes well, to first acknowledge the child, you need to call wait on the child process. So wait has the following API, takes only one argument, a pointer to an int, and that's the address to store the wait status of the process. So it will actually assign a value to it, and it will return the process ID of the child process if it's successful. So right now it will return -1 if it fails. If there's two versions of wait, there's a blocking one that will wait for that child to terminate, and a non-blocking one that will just poke it and be like, hey, are you dead yet? Yes or no. Have you terminated yet? Yes or no. And it will return immediately. So we'll see how to do that later. For now, it will never return 0. It will block until that process ID has actually terminated or give you a failure. So that wait status contains a whole bunch of information, including that exit code, which is what it returns from main. So you can use man wait to figure out all of the macros to query the wait status. We'll have an example that will show what it does. So before we create weird zombies and stuff like that, let's do the simple example. So here is our program that's going to use wait, and I'm going to artificially put in some sleeps just to make things more consistent. Not guaranteed to always be consistent, but I'm more likely to, which is good enough for the purposes of the lecture. You should not be using sleep to guarantee that things run in a certain order. We'll see how to ensure order later in the course. But if I run this program, again, I like arguing that just process 100 starts executing the main function. The shell would create it or something else. I don't really care right now. Just process 100 will execute main. And then the first thing this process does is call fork. Lucky for us. So this will create a new process 101. That is an exact copy of process 100. So it will have the same program loaded, and it will resume from returning from fork. So in process 100, what does fork return? 101, right? In process 101, what does fork return? 0. Which process executes next? I have no idea. So you have no idea, but one process will execute next. We'll just assume a single CPU for now. So in this case, we'll just assume these two processes. If process 100 executes next, well, it will go ahead, create a variable called PID, and then assign the return value of fork to it. So PID will be equal to 101. So process 101, PID won't be able to -1 because there's no error, so it will fall into this else branch. And then it will print calling wait. So it will print calling wait, create an int called wStatus, and then do that system call wait, where it gives the address of that int to wait. Wait is going to be a blocking system call. So process 100 will not resume execution until process 101 is done, has terminated or returned from main or called exit. They all do the same thing. So process 100, if it executes all the way, it will make it to this wait, and it will be stuck here, blocked, waiting for process 101 to perish because it is its child. So now the only process that could execute is process 101. Its process ID, well, sorry, let's back up a bit. So fork returns 0, so it would also create a variable called PID, which it assigns the return value of fork, so it would be equal to 0. So process 101, PID will be equal to 0, so it will go into this if statement, and then sleep for 2 seconds, which will just literally put this process to sleep for up to 2 seconds. And then sleep is also a blocking system call. Hopefully it actually just puts it to sleep for 2 seconds. Once sleep returns, so it would return continue execution. Because this is within one process, it is consistent. So it took this if branch, so it will not take this else branch. So it will fall all the way to return 0, which is this exact same thing as exit 0. All right, so this process 101 is going to terminate. And then after process 101 terminates, process 100 will wake up. So it will unblock from wait because now my process is done. And then it will return from this wait. It will return the process ID of the child that has terminated. So it should return 101 in this case. And then it fills this, it assigns this integer with a whole bunch of information, including the exit code. So you technically need to use a whole bunch of macros from the man page to figure out why it terminated and get some information about it. So there's several reasons a process can terminate. For now, we'll just assume it has to have exited to have terminated. So if it hasn't had, so you can use the macro to check if exited and give it that W status that was assigned from the wait system call. So if exited will return 1 if indeed it terminated by exiting. If it returns false, I just exit this process 100 with the error code eChild because I have no idea what's going on. It's an unhandled case. But for now, I'll assume that it has to have exited. So when it exits, I do printf wait return for an exit process. PID is that value I got from wait PID. And then its status should be whatever it returned from main. And in this case, if I want to get the exit status or whatever value it returned from main, I use that w exit status macro, give it the integer, and it will extract out whatever value that program returned from main, in which case it should be 0. So if I go ahead and run this wait example, then I see calling wait. That's from my main process. It waits 2 seconds for my child process to terminate. So this answers your question over there, like how would I write my shell? How would I prevent it from continuing? So what my shell does is when I start my program, it would fork, exec it, and then wait for it to actually finish before I'm allowed to type more on my shell. So now we can actually create a scuffed version of a shell if you really wanted to. So the parent calls wait. It blocks for, in this case, 2 seconds because it's waiting for the child to terminate. Then once the child terminates, wait returns, it's unblocked. Then I see wait return for an exited process. In this case, whenever I ran it, I got 8,122 and then a status equal to 0. So questions about that? Neat. So just to verify that, I'm actually reading some values. After sleeping in the child, I could return, I don't know, the value 42 or something like that, which will, since I'm returning from main, this is the same thing as exit 42. So just to verify, I'm acknowledging my child, and I'm actually getting that value in the parent process. I can recompile, run it again. I see calling wait for 2 seconds, and now I see that the status I got from the child was 42. So it's whatever it exited with. So that's my acknowledgement from the child. Fun, right? So any questions about that before things get weird? Yeah.
It says on the slide we can use wait PID to wait on a specific child process.
Yeah.
How would we get the PID of the child process we want to wait for before in the parent process?
So, yeah, the question is, what's the slide? So there's also a version of wait. So this wait, so this wait will wait for the first child to terminate of any of your children. In this case, I only have one. There is another system call called wait PID, where you can wait on a specific child. So wait PID, its first argument is the process ID of the child I want to wait for. And then this int stat location, that's that pointer to W status. And then there's a few other options we can do. So if I wanted to wait specifically on my child, the question is, how do I know its process ID, right? Well, in this case, in the parent, which is process 100, what's its value of PID there from the fork? Yeah, it's the process ID of the child. So if I wanted to specifically wait on my child, in this case, instead of just wait, I could do something like wait PID. In this case, I could give it the process ID of my child, which is what was returned from fork, conveniently enough. And then I can give it W status. And then the optional argument I can just give as null. So I could do something like that. That will actually just do the exact same thing, where, because I only have one child, just waits for my one child to exit, but I'm specifically telling it to wait for that child. So might be useful if I have to wait for multiple children or something like that, and I want to wait for a specific one, but don't have to. All right, any other questions with that fun stuff before things get strange? All right, let's start us down the rabbit hole. So, a zombie process. Zombie process is just waiting for its parent to read its exit status. So, a zombie process means that process has terminated, so it has exited, but it hasn't been acknowledged yet. So no other process has called wait for it. So why this is important? Well, you might think that that process might have an error in it, and that parent might have an error in it where it creates a child and then ignores it, and it's neglectful. and that child may have an error, and if it has an error and you don't read it, how do you tell it has an error? Something bad probably has happened, and you should probably handle it. So you should probably be a good and responsible parent. So the operating system has a way to kind of nudge your process to try and be a responsible parent, because as a responsible parent, you should always acknowledge your child. So the operating system has a mechanism where it can interrupt your process and say, hey, your child has terminated. You should probably acknowledge it, please. We'll see what that exact mechanism is in the next lecture, but it is also basically a suggestion, so you are free to ignore it, and that is also the default behavior. So the default behavior is if your child process terminates, operating system will poke you, and you will immediately ignore it. So it's technically a basic form of inter-process communication called a signal. It's basically like a user-level interrupt. Again, we'll see it in the next lecture. But the reason this is important that because if you are a neglectful parent, the operating system has to keep that process around as a zombie process until it's acknowledged. So again, it's terminated, it can't run anymore, but the operating system can't get rid of it because it needs to be acknowledged by something. If the parent just completely ignores it, it's a zombie process and it needs to wait to get reparented, which we'll see in a bit. But let's make sure that a zombie process actually exists. So here is our example. So in this example, all right, we can ignore that function. So I just have a function I wrote to get to read the proc file system and read the state of a process. We'll ignore that for now. Again, we'll just assume process 100 got created, and that is the process running main. Immediately, it calls fork. So we create a new process called 101. Again, doesn't have to be sequential, but to argue about it, typically it's the easier thing to do. So in process 100, fork returns 101. And in process 100, fork returns 0. I don't know which one is going to return from fork first. I don't know which one is going to continue running. I don't know if they'll get switched or they'll be interleaved or whatever. So I'll just assume process 100 goes first. So fork returns 101. So it creates the variable called PID, and it is assigned to 101. So it's going to fall into this else statement. The parent is going to sleep for 1 second. And then it is going to read the child's process state. So what the state of that process is after a second. It's going to check if it returned an error. It will not return an error. Whoops, I don't want to get rid of that code. So it hopefully will not return an error. And then it will sleep for another 2 seconds. So when it wakes up from this sleep, it will have slept for a total of 3 seconds on the wall clock, and then it's going to read the process's state again, and then just terminate. So any questions about the parent? So it's going to read the child's state after a second, and then another 2 seconds after that, or at 3 seconds approximately. All right, so we're all good with the parent. So what is the child going to do? So fork returns 0, so it's going to create a variable called PID. It's going to assign it equal to 0. So it's going to fall into here. The child is going to sleep for 2 seconds, then wake back up, and then fall through, and then just return from main, so it's going to exit. So approximately, the child is going to only exist for 2 seconds, right? So the child's going to exist for 2 seconds, and the parent is going to check the state of the child after 1 second, and then after a total of 3 seconds to see what its state is. At 3 seconds, the child should be dead, right? So if I run this, I can see that indeed the child's process state after 1 second is sleeping because only a second has passed. It's in that middle of its 2 second sleep. And then when the parent wakes up again after 3 seconds, reads the state again, and the state is indeed a zombie. So it means it has terminated, but I have not called wait on it yet, right? So the process ID of that child, in this case, in my example, it's 101. The operating system is still keeping track of process 101, and it has stored its exit status at return from main, in this case is 0. So it can't completely remove that process ID 101 because no one has acknowledged it yet. So it will still be available, and it will be in this zombie state until some poor soul, someone acknowledges it, hopefully the parent. So any questions about a zombie process? All right, so we got to get into the other side. So an orphan process needs a new parent. So the child process lost its parent process. So the child process still needs some process to acknowledge its exit. And what the default rule is the Linux kernel or Unix kernels in particular really want to maintain this parent-child relationship. So if your parent has terminated, no longer exists, then the kernel will get you a new parent. So it will reparent you, or you can think of like, you get adopted by something else. The process is literally called adoption. So the operating system will reparent you. By default, it reparents you to a init. That is process ID 1. And then the init process is now responsible to acknowledge the child. So init actually has two jobs. It's responsible for creating all the processes on your machine, either directly or indirectly, and then also kind of being like the orphanage that cleans up all of the children that come to it. So init, if it's written correctly, it should also acknowledge any children that it adopts. So let's see how that works. So we have an orphan example here. So in this program, again, we start off with fork. So I'm going to argue that we have process 100. Wow, I can't type. Process 100 starts executing main. First thing it does is call fork. So that would create process 101. So I'll shortcut this a little bit. In process 101, it'll create a variable called PID. It'll be equal to 101. In process 101, it'll create a variable called PID equal to 0. So in this case, let's assume the parent executes first. So the parent is going to sleep for 1 second in total and then exit. So the parent's only going to exist for 1 second. Then what the child is going to do is go into this if, and then it's going to print off its parent's process ID, which should be whoever just called fork, right? Because my parent should last for at least a second. This should happen pretty much immediately. So I should get the process ID of whoever just created me. But then I sleep for 2 seconds. So my parent dies after 1 second. I wait 2 seconds, and then I print who is my parent now. So I would have been adopted by some other process. So let's see that that exists. So let's run our orphans example. I get process ID of 8,703. Then I see I got control back to my terminal. That's because my shell is waiting on the process I originally ran. In that argument, it was process 100. So after a second, when process 100 terminated, my shell gave me control again because what I was running is dead. But the child was still running in the background. It was still connected to my terminal. So after 2 seconds, it yelled out to me from beyond my grave and printed off its new parent, which is 1,683, which is not process ID 1. So I did not lie to you. We can figure out what, we can figure out what this process is. So process this status is systemd, which is the same name as process ID 1 init. So happens there's a process manager specifically for your user, and you can actually opt in to become the orphanage where orphan processes will get adopted by you instead of init. So that is one thing systemd does. So it's like kind of manages processes for your user. It has a gruesome name. So I called process 1 like the orphanage. That's a good name for it because it gets all the orphans. But its official name is the Reaper, like the Grim Reaper, because it kills everything that comes to it. So by default, process ID 1 is the Reaper because it kills all the children it gets. Yeah, again, your Google searches get weird. And you can opt in. So any process can opt in to being a sub-Reaper, which means any grandchildren that get orphaned from you go to you instead of init. So you get to kill them instead of init. So you can become a Reaper. Again, I did not make up these terms. Do not blame me. But if you need to, perfectly valid Google term, how to become a Reaper to kill all my children. Perfectly valid Google search. Might get you put on a list somewhere, but if you just say, just add on operating system at the end of it and it will be fine. All right, any questions about our fun sub-Reaper or anything like that, or our orphanage or any weird things? Yeah?
How do you set it to be the orphanage?
How do you set it to be an orphanage? You will figure it out in lab 2. So lab 2, you will, one optional component of lab 2 is to become a sub-Reaper and kill children. So I will not, again, if this was a different course and not operating systems, I would be in jail. So thankfully, we're safe in operating systems. All right, any other questions about zombies or orphans or anything like that? Yeah. Sorry? How do you acknowledge your child? You call wait on it. So that wait system calls how to acknowledge your child, and then as part of what gets set from wait, you get its like exit status and a whole bunch of different things. So that's acknowledging it is the wait. So writing a good program, if you fork, you should, unless you have a good reason to, you should acknowledge your children. So you should always wait on them and clean them up to make sure that they're not killed by anyone else. So you should kill your own children. Don't let someone else kill your children. Again, weird. Yeah?
So does that mean in like the other examples there were just zombie children or like orphans or that kind of thing?
Yeah, so that's a good question. So in the other example, so in this zombie example, right? I never acknowledged my child. So I read its status, it was a zombie. I never acknowledged it, and then I died, right? So technically, that child process is now a zombie right when I checked it, right? And then I died. So when I died, it also became an orphan. So that process is now simultaneously a zombie orphan. So it's both a zombie and an orphan. And then because of that, it's an orphan, it gets reparented, for argument's sake, to init. And then init adopts it, and then init would wait on it and clean it up if init is written correctly. So it would briefly be, when this parent exits, it would briefly be an orphan zombie. Then it would get adopted by init, and then init would wait on it, so now it's cleaned up and that it's no longer a zombie, is how things should work. Yeah?
So maybe this is not important level of detail, but how does the wait function actually acknowledge the child process, other than just, because we read the exit status in this example as well, but we haven't quote unquote acknowledged it, right?
No, so returning from wait, well, in this example, we don't return from wait, so we don't acknowledge it as a zombie.
Right. So what does wait do to like acknowledge the child process?
So wait, what does wait do to acknowledge the child process? So wait blocks until it's terminated, and then it will extract some information out of its process control block, like the exit status and why it exited, into this W status variable, in which case we've extracted all the information, we've acknowledged it. So after wait returns, let's say we waited on process 101, after this wait returns in 100, process ID 101 now no longer exists. It's completely cleaned up. That process ID is now free, and now the operating system can actually reuse things. So if I don't acknowledge it, and I just create a whole bunch of processes and never acknowledge them, at minimum, their process ID still exists, and I just create zombie after zombie after zombie after zombie, and eventually I might run out of process IDs. Right? All right. So any fun things knowing all the bad things we learned this lecture? Anything you want me to do to definitely end the lecture? So one thing I could do. Oh, what example? Let's go back to fork example. All right, so I'm lazy. I'll just return 1. All right, so fun things I could do. Wow. What's that do? Yeah. Yeah, it's so fun it even has a name. So its name is a fork bomb. But what's it do? So, yeah, so let's say, argument's sake, process 100 starts running this. Right? Process 100 starts running this. Okay, well, while true, all right, goes into the loop. We create process 101. And now both of these would go in the loop again, right? So next time through the loop, 2 processes called fork. So how many new processes get created in the second iteration of the loop? 2. All right, what about the next iteration of the loop? 4, then 8, then 16, then 32, then 64, then blah, blah, blah. So let's have fun. So printf, I forked up. So let's just add a bit of flavor to it. So if I compile and run this program, something bad should happen, right? So also, again, if you log on the school's machines, probably don't run this. So don't do what I do. But let's try run it. So if I run it, I see eventually my operating system protected me a little bit. There's a bunch of numbers that flashed by, and then I got -1. So -1 means fork failed. So one of 2 things happened. Either my operating system was smart and was like, this guy's an idiot. I'm going to not let him make any other processes and stop him. Or I have ran out of process IDs, and I can now no longer make processes. So if I press this plus button, oh, and things are getting warm. So if I press this plus button, this should launch a new shell, right? So if I press this plus button, if I press this, uh-oh. If I have any input, the window is not responding. Close? Oh. And then we can check if anything bad has happened. Turns out my system kind of recovered. Is there anything bad? No, that's not bad. So different things happen in different years, all sorts of different things. And then, yeah, I think that, well, that pretty much crashed everything. We're out of time anyways. So you can try and run that on your